Here are solutions to homework set number 11 for ECE 463-663 Modern Control. This homework looks at designing feedback controllers using LQG techniques when you have servo compensators. Now the first problem is for the cart and pendulum system. So what I want is to come up with a way to force an inverted pendulum to go from 0 to 1 balanced, but use optimal control methods to find the feedback gains and also have it able to reject a constant disturbance. So to do that, you start with the system dynamics, add a servo compensator, find the feedback gains using LQG techniques, and let's go over here. Kind of one way to do that is kind of trial and error. So LQG is just a way to find feedback gains. Now let's put this over here. So I've got the system dynamics. I'm going to augment the system with the servo compensator, specify the desired response, and then find the feedback gains instead of using pole placement using LQG. So these are the states. I've got the 4 states of the plant and the servo compensator. I would start out by just weighting the servo compensator states. The output is in blue, the desired response is in red. It's too slow. So what you do is you crank up the gain. So I crank up the gain. I get a quicker response. Once you're a little bit too fast, I can add some friction. So this is the servo. The input of the servo is the first state. So if I try cranking up that gain, I've got spring. This looks like friction. Drop down a little bit. It's not too bad. So what I might do is have this as my cue. And that's kind of the approach of servo designing feedback gains using LQR techniques. It's kind of trial and error. These are knobs you can adjust as you play with them. Bigger gain on the servo gives you faster system. The input of the servo, which is the plant's output, looks like friction. Play with it until it's a decent response. So when you do that, eventually you're satisfied. I wound up with 30-30 first time I tried it, giving you the blue response. Once I get my feedback gains, I can then check it on the nonlinear simulation. So once you pick your feedback gains, these are the gains for the states, the servo compensator, put them together, and there's your step response. So again, not a whole lot different than pole placement. The advantage is just another way to find your feedback gains, KX, KZ. Advantage being I only have 2 knobs to play with rather than having 5 poles to play with. Having 5 poles to place anywhere you want is a little bit daunting. It's a lot easier just adjusting 2 gains. And when you do that, I did place the pole somewhere. If I go into MATLAB, that's where I put the closed loop poles. Nothing magical about that pole location other than it gives me this step response. So that was the first 3 problems. The last 3 kind of illustrating the approach, LQR techniques design approach. Repeat for the ball and beam system. Now for a ball and beam system, I've got a beam that I can apply torque to. The ball then rolls around based on gravity. I want to get the ball to go to a certain spot like 1. Come up with a way to do that using a servo compensator with the feedback gains found using LQR techniques. So the procedure is kind of similar. Start with the system dynamics, augment the dynamics to add the servo compensator, find the feedback gains, only now using LQR techniques. It's kind of similar to what we did before. It is kind of a trial and error basis. So if I take the system dynamics, the servo compensator, I want to play with these gains. I'd start out with a weighting on the servo state right here. Find the step response. So here's the plant, here's my desired response. A little bit slow. So crank up the gain. Gives you faster system. maybe a little too fast. Get the system about the right speed. I want to get rid of those oscillations, so I can weight these states. If I weight the output y, let's make that 100, see what that does. Maybe a little bit better. If I weight the second state, that is beam angle, not much difference. Weight the third state, that's velocity. That's got a big impact. Weight the fourth state, and these are just knobs to play with. Maybe the third one. That seemed to have the best impact for getting rid of the oscillations. Speed it up a little bit. Okay, not bad. And it's just kind of subjective. At what point is it close enough? A little bit better. That'd call it done. Once you find Q, you get your feedback gains. That kind of drops out automatically. LQR, find your feedback gains. I called it K5. If I, plot the step response to linear system, that's what I just did. Red is the desired response, blue is the actual response. I can then check it on the nonlinear system. So going to the nonlinear system somewhere, here it is. Take the gains that I computed, plug them in for Kx and Kz, that's the gains for the servo compensator, and try it. And here's your step response. So LQR isn't a whole lot different than pole placement. The advantage of LQR is you tend to wind up with smaller feedback gains. You can handle multiple inputs, which doesn't really affect this homework set. But really, it's just a tool. If the tool helps you, use it. If it doesn't help, don't use it. You've got two tools now, pole placement, LQR techniques. Both approaches are perfectly fine for finding feedback gains. Whichever one works best for you is the one you ought to use. That's homework set number 11 for 463 Modern Control.